So when you're given a problem like this, what you want to do, if necessary, is to factorize the denominator. So if I take this x squared minus x minus 12, some scratch work here off to the side, x squared minus 1x minus 12, what we can do is we can play this little game. And you take the negative 12 and you put it in the top. The negative 1 goes in the bottom. Now find two numbers here and here, that if I take those two numbers and multiply them, it's negative 12. But if I take those same two numbers and add them, it's negative 1. With some trial and error, you'll see that the numbers are 4 and negative 3. Negative 4 times 3 is negative 12. If you add them, it's negative 1. These two numbers are the winning combination, and these two numbers are what you want to put down here. Does it matter which one you write first? No, as long as you make the 4 negative, because if you make the 3 negative, you lose this condition down here. So I would always factorize this if necessary. How do I know that this is correct? I can do this out loud or just visually. How much is x times x? X squared. How much is negative 4 times 3? Negative 12. What do I get if I multiply these? If you multiply those, it's negative 4x. And these guys, positive 3. How much is negative 4 and positive 3? Negative 1, which is right there. That's how I know that this is correct. And what's even the point of doing this? What's the point of taking the bottom and breaking it up into these pieces? What you want to do is you want to set the denominator equal to 0. If I set the denominator equal to 0, and if I solve that equation, I can do this quickly because I have factorized this denominator into these pieces. Set each of these factors equal to 0 and solve. If you solve these one-step equations, you will have discovered what we call the vertical asymptotes. I'll just abbreviate it V.A. These are the vertical asymptotes. These are the lines that go up and down like dotted when we make our picture at the end of this video. For now, set the numerator. Set the numerator equal to 0 and solve. And what you get in return is called the x-intercept. So when you let the bottom equal 0, you discover the vertical asymptotes. When you set the top equal to 0, you discover the x-intercepts. Now, for the more complicated case, the horizontal asymptote. The horizontal asymptote is discovered by comparing the degrees of the top and bottom. If you look at the numerator, the degree of the numerator is 1. The degree of the denominator is 2. The bottom has a larger degree than the top. Anytime the bottom has a larger degree than the top, then automatically your horizontal asymptote becomes y equals 0. That is always the case, where if the bottom has a larger degree than the top, then the whole function has a horizontal asymptote of y equals 0. What would have happened if, let's say, the original problem said this instead? What would have happened if it was actually the degree is 2 and the degree is 2? What would have happened if the degree of the top and bottom were the same? Then the horizontal asymptote would have been 1, because you take this number and you divide it by this number. Whenever the top and bottom have the same degree, you divide the leading coefficients, 1 over 1, and that gives you the horizontal asymptote. What if the problem said 4x squared over 7x squared? Then in that case, the horizontal asymptote would have been y equals 4/7, and so on. So let me wipe this off. Let me get rid of this. Oh, you might be wondering, what happens if the top has a larger degree than the bottom? Let's say the top has a degree of 3 and the bottom has a degree of 2. If the top has a larger degree than the bottom, then in order to find your asymptote, your horizontal asymptote, you would have to go long division. You'd have to go long division with the top divided by the bottom, and whatever you get here would be your asymptote. And as a matter of fact, under that condition, it would not have been horizontal, it would have been a slant or oblique asymptote, or perhaps something worse. But we're not dealing with that because the problem said x minus 1. So let's go back to our main problem, as is. So these are the vertical asymptotes, our x-intercept, and now we have our horizontal asymptote. What we can do now is we can open up the x and y axis. Let's say we go down here. Let's go a few spaces each way. And what we're going to do is we're going to plot the information that we have just now discovered. And so we have here a vertical asymptote where the vertical asymptotes were at 4, 1, 2, 3, 4. So let's make it dotted like this. Teachers like when the asymptotes are dotted. And then we have another vertical asymptote at -3. Okay, there it is. We have a horizontal asymptote of 0. I'll just trace above the x-axis because that's y equals 0. And then we have an x-intercept at +1. So I'll put a point right there. Sure. And just as a quick FYI, what about this? What about the y-intercept? How do you find a y-intercept? To find a y-intercept, you let x equal 0. Plug in 0 for all the x's. If I put 0 there, this disappears. If I put 0 there, this disappears. This disappears. I would be left with -1 over -12. So my y-intercept is -1 over -12, which is 1 over 12. And so it's 0, 1/12. That is a point that is barely above the origin. I mean, 1/12 is a really small decimal. So the y-intercept is like right there. It's barely above 0, 0. Anyways, how do I actually draw the shape? All I've done is lay down the foundation. I have the asymptotes. I have a couple of points. How do I actually make the picture? I would rely on making a table of values. What numbers should I use for my x's? Pick numbers that are close in between and around the vertical asymptotes. For instance, this is -3. Behind it, I have like -4. This is -3. How about in between -3 and 4? I go like -2, -1. I already have 0 and 1. How about like 2 and 3? And then maybe something after the 4. How about like 5? The point is, you take these numbers. For instance, you take -4 and you plug it in there in parentheses carefully on a calculator. The -4, when you put it there, put it in parentheses because it's going to be squared. And put it there as well. You're going to get back a number. Whatever that is, you plot it on this grid. And then do the same for the -2 and for all these guys. The more points you get, the more obvious it'll be how to actually connect the points. And I can tell you here with this purple pen, with this purple marker, that the graph would look like this. The graph would look like this here. And it would look like this here. Something like that. And then it would look like this right here. And then for the last part, they want us to discuss sort of some limit notation. So let's see if I can write them right here. So for instance, what would be the limit as x approaches 4 from the right of f of x? So when it says f of x, it refers to the name of this picture. This graph is called f of x. That's all that means, right? When it says f of x, it just means the equation and the graph that goes with it. So what are we approaching? We're approaching 4 from the right. That's what this means. This means 4 from the right. Well, where exactly is 4? 4 is 1, 2, 3, 4. Here's 4. Here's 4 right there. But from the right means from this side. So I have to jump on the purple roller coaster and I have to come closer to my hand from the right-hand side. And as I do this, look, what's happening? What's happening to my black pen? It's going up, 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 up. And because the pen was climbing up, I would say that this equals positive infinity. Because I was getting, here's 4. I was getting closer to 4 from the right. And as I get closer to 4 from the right, my pen is physically going up. Look at the pen go up, 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 up. That's infinity. What about this one here? The limit as x approaches positive 4, but from the left. Okay, here's positive 4. From the left is on this side. Let me jump on the purple roller coaster. As I trace this, I'm getting closer to my hand, but in which direction is the pen going? The pen's going down. It's like off the camera. The pen's going down, 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 down. That's why this is equal to negative infinity. What if we get closer? What if we approach -3, but from the right-hand side? Let's see. Where is -3? It's over here. I'm approaching it from the right-hand side. Okay. Here's from the right. My pen is getting closer to my hand, and I'm getting closer and closer. But what's happening? I'm suddenly going up, 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 which is why the y-coordinates go up. You see, this tells you what the x-coordinate should be, and this tells you what is happening to the y-coordinates. This describes your x-coordinates, and this describes the y-coordinates. This describes the x coordinates. This describes the y coordinates. One more, the last one. How about if we approach -3 from the left? Okay. Well, -3 is here. From the left is on this side. Trace the purple function. I'm getting closer to -3 from the left. What's happening to the pen? It's going down, 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 down. The y coordinates are going toward -infinity. So apply these techniques to other exercises and let's see how it goes.